So now let's talk about the different types of intermolecular forces. We're going to start by just sort of defining what they are, and then we'll go through and talk about each one in detail. So our strongest intermolecular force is our ionic. Then we have ion-dipole. We have dipole-dipole. Then we have one with a very unfortunate name. We call it hydrogen bonding. And why is that an unfortunate name? Well, you may recall in the last video I talked rather extensively about how intermolecular forces are not bonds. And you can see the name that's included here. Unfortunately, this one has the name hydrogen bonding, even though, and let's emphasize this again, it's not an actual bond. And then our weakest is either, we call it London dispersion, or van der Waals forces. All right, so let's start by talking about ionic. So ionic intermolecular forces are by far the strongest. They often lead to melting points nearing 1,000 degrees or even higher. And the reason for this is ionic intermolecular forces come from ionic compounds such as sodium chloride. So sodium chloride, we know, is made from a sodium ion and a chlorine ion. And you can see in this picture an example of what that could look like. And so because the ions are full charges, you end up with a very, very strong attraction between them. And for a lot of these ionic compounds, you have these very intricate and very regular crystals or lattice type structures, as you can see here. And in these molecules, these ions are held extremely tightly together with essentially no movement. Now, one thing you might find surprising in the picture is the size of the ions. And you can see here the chlorines are showing up a lot larger than the sodiums. Now, if you recall our periodic trends, if you look at the third row on the periodic table, sodium being on the left is larger than chlorine. But here we're dealing with a sodium ion. And if you think about the electron configuration for the sodium ion, that's 1s2, 2s2, 2p6. So that third energy level is gone and actually ends up making the ion quite a bit smaller. Our second intermolecular force is the ion dipole. So you recall we previously talked about dipoles, and we said a good example is something like water, where the oxygen is more electronegative than the hydrogen, and these bonds are polarized towards the oxygen. And so overall, the water molecule has a net dipole, which shows us partial positive charges on the hydrogen. That's what the lowercase delta stands for. And a partial negative charge on an oxygen. And what we mean by partial is it means that those ions have some charge character, but they're not a full charge. But ion-dipole interactions are extremely important when we deal with aqueous solutions. Because we know that most ionic compounds are soluble in water. And so the interaction on one level we can see is the delta plus from the dipole is attracted to something with a full negative charge from the ion. So what happens when we add something like sodium chloride to water? Well, what happens is the sodium and chlorine ions dissociate from each other. And so the sodium goes off with some water molecules. That should be a 4 there. And the chlorine goes off with some varying number of water molecules. So what does that look like? Well, if you think about this structure, we have this delta plus end of water with the hydrogens. Those are going to be attracted to the anion. Whereas the delta minus end, the oxygen, will get attracted to the cation. And so we often show this by dotted lines to show that it's an attraction but not an actual bond. So that sodium, which is positively charged, the oxygens are negatively polarized, are going to attract to each other. And that's what helps the sodium chloride molecule to dissociate. In other words, the two ions separate from each other and allows the sodium chloride to be soluble in water. All right, we can go to our next attraction, which has a lot of similarity. Dipole-dipole. Not as strong as ion dipole, but this exists between two neutral but polar molecules. So because these aren't full charges anymore, these attractions are going to get weaker. But what's happening is pretty straightforward. We have one molecule that has its delta plus, delta minus based on the dipole from the unequal sharing of electrons. And it's going to attract to the delta plus, delta minus end of another molecule. And then this can just go on indefinitely. Now there's varying degrees. So if we have a larger dipole, based on larger electronegativity differences, then we have a stronger attraction. Now, a variation of dipole-dipole interactions is known as hydrogen bonding. And it's actually a special case of dipole-dipole. And it happens specifically when we have an HF, HN, or OH bond within our molecule. And so even though these are hydrogen bonds, these actually end up being a bit stronger than our normal hydrogen bond. And one of the ways we can see that is to compare chloromethane, CH3Cl, with a molecule that has a nitrogen as well as an alcohol. So if we look up the electronegativities of these different elements, what do we find? Well, we're not going to worry about the carbon end of this molecule because that's the same for all three. But let's look at the other two, or the other atoms, the chlorine, nitrogen, and oxygen. So chlorine has an electronegativity of 3.16, nitrogen is 3.04, and oxygen is 3.44. So if these were purely dipole interactions, then we would expect the highest boiling point to be the one with the strongest dipole, and the one with the strongest dipole would be the one with the biggest electronegativity difference. Because recall, the electronegativity for carbon is about 2.5. So the largest difference is with oxygen, and that gives us a boiling point for this compound of 64.7 degrees. The next largest difference, though, is with chlorine. But it turns out, because of this hydrogen bonding, the molecule containing the nitrogen, which should have a smaller dipole, turns out it actually has a stronger attraction. So hydrogen bonding in most cases actually ends up being a stronger attraction than dipole-dipole. But it is largely just a special case of a dipole-dipole interaction. Now, hydrogen bonding ends up being extremely important biologically. And here's an example of that. So it also does have a significant role with proteins. And I don't know where my bond keeps going. But if we look at these two molecules, these may not be familiar to us at this point. Or maybe we will be familiar with them. And then I'm just going to draw sort of a green squiggly line here. That means these are connected to other stuff beyond that. So what do we have here? On the left we have guanine, On the right, we have cytosine. Where do we find guanine and cytosine? Well, guanine and cytosine are two of the base pairs that make up DNA. And if you look carefully at these, we have an oxygen up here, which can form a hydrogen bond with the hydrogen that's bonded to this nitrogen. The nitrogen here can form a hydrogen bond with this NH, and this oxygen forms a hydrogen bond with this NH. So we have three hydrogen bonds that are holding the cytosine and guanine base pairs together. Now, the same type of thing also exists for the other combination, adenine and thymine. That's why if you've ever taken a biology or a chemistry course where you looked at amino acids, that's why C always lines up with G and A with T. It's because of this issue of hydrogen bonding. But in addition to that, it's not just that the hydrogen bonding helps hold these together, but the hydrogen bonding is the only thing that holds the entire double helix in DNA together. And so without these hydrogen bonds, there would be no double helix for DNA. All right, finally, our last intermolecular force are the London dispersion or van der Waals. And these are very, very weak. London dispersion forces happen when we have no dipole existing within the molecule. So not only is there not the full charge of an ionic compound to attract two molecules, we don't even have the partial charges that we get in a dipole. But we know that there still has to be some force attracting these molecules. How do we know that? Well, if we have a carbon containing molecule with 5 carbons, C5H12, and we're just talking about 5 carbons straight across. Pentane has a boiling point of 35 to 36 degrees Celsius. But if now instead of stringing 5 carbons together, we do it with 40, this is known as tetracontane, we can actually get a compound that's a solid and has a melting point of 80 to 82 degrees Celsius. Now, it's still very, very weak. And to give you an example idea of how weak this is, think about this. In order to get to a melting point of 80 degrees, we've got to put 40 carbons together. If you compare that to an ionic bond, anyone remember what the melting point of sodium chloride was? So the melting point of sodium chloride with just 2 atoms is 801 degrees Celsius. So we can see here just how weak London dispersion forces are. But they still matter, and they're still critically important. So if there's no actual dipole, how do these molecules get attracted to each other? Well, let's say this is our molecule. Here's our nucleus. And we know, based on what we learned about quantum mechanics, that the electrons are randomly distributed. Well, maybe at some point we get to a time where, even though they're randomly distributed, they're more in one area than another. And that's what we have here. You can see that the electrons are more on one side of the molecule than the other. And so we refer to this as a temporary dipole. Why temporary? Well, all it takes for this dipole to go away is the electrons moving somewhere else. Once that happens, then the dipole's gone. But what this can cause is if there's another molecule nearby, these electrons can then push the other electrons to the other side, and we induce a dipole in the next molecule. But again, these are much weaker attractions. And we can do even a closer comparison than what we had before, which would be to compare ethane and methanol, two molecules that are very similar in size, similar in number of atoms, similar in weight, but ethane has a boiling point of negative 88 degrees Celsius, whereas methanol has a boiling point of 64.7 degrees Celsius. So for molecules that only have van der Waals forces, the main thing that is going to control is how polarizable a molecule is. So polarizability is the ease with which charge distribution can be distorted by an electric field. So the first point is the more electrons we have, it might make sense that as we have more electrons, it's more polarizable. And the further we get away from the nucleus, the more easily they can be polarized. So one place that you can see that is, for example, in the halogens. So the halogens are all relatively nonpolar molecules because they're just the same atom bonded to itself, so there's nothing to polarize it. But as we add more electrons, which we do going down this direction, as we get further away from the nucleus, we can polarize more easily, and so fluorine has and these are boiling points. Fluorine has a very low boiling point, close to negative 200, whereas chlorine is much higher. Bromine is actually a liquid at room temperature, one of only two elements that is a liquid at room temperature. And then iodine is one of the few nonmetals that's actually a solid at room temperature. So the more electrons we have, the more polarizable the molecule is. As a molecule gets larger, it's also more polarizable. The more atoms we have, the more opportunity there are for the molecule to be polarized, and we get better overall attraction. So any hydrocarbon molecule, a molecule containing just carbon and hydrogen, is a nonpolar molecule. But as you can see, the more carbons we add, the more opportunity for it to be able to polarize, and the higher the boiling point. And we saw this also with the tetracontane. Eventually you can get quite a bit higher. But with a nonpolar molecule, it takes a lot more work, a lot more atoms to get there. And finally, the shape matters. The better the molecules can pack, that means there's more surface area for interaction, and they get a higher overall attraction. So this is known as a line structure. It's the way we draw organic molecules in shorthand. Every vertex here represents a carbon. So here we have an 8-carbon molecule. The hydrogens are then just assumed to be there. Here's another 8-carbon molecule, but you can see it's arranged in a different way. And so the way that this works is that when we start to have this branching, the molecule can't pack together as well. And since it can't pack as well, there's less surface area for it to attract, and the boiling point ends up going down. Now, it's important to remember that all molecules actually have London forces. It's just in many cases, the other forces are much stronger, and so they win. And so we can see a couple examples of that here. So if we look at this sequence of molecules, they all have OH groups in them, so they're all going to have hydrogen bonding. So because they all have OH groups, that OH group will allow for hydrogen bonding. So in that respect, they're going to be very similar. But the place that these are going to be different is the length of the carbon chain. So here it's just 1 carbon, here it's 2 carbons, and here we have 3 carbons. So as we go down through this list, the H bonding stays pretty much the same. There's 1 OH group. But the London forces increase. And so do we end up with an increase in boiling point as we go down this list? In fact, we do. So before I end this video, let's do one practice problem. And that's I'm going to give you a series of compounds, and I want you to try and rank them in order of boiling point. So what we would need to recognize for each of these molecules is what is the dominant intermolecular force. So barium chloride is an ionic compound. Any ionic compound is going to have an ionic intermolecular force. Carbon monoxide is going to be a dipole. HF, that's one of our three groups that can form hydrogen bonds. And both hydrogen and neon are completely nonpolar and have just London forces. So how would we rank these? What would be the highest? What would be the lowest? Well, we know barium chloride, being an ionic compound, is going to definitely be the highest. Next would be the hydrogen bonding. Followed by the dipole. Between hydrogen and neon, one of those is larger than the other and therefore more polarizable. So the neon should have a higher boiling point than hydrogen. Now, if we go and look up actual numbers, is that what we find? So we find hydrogen is the lowest at -259. Neon is next at -248.7. Carbon monoxide comes next at -205. HF is at -83. And barium chloride, the ionic compound, is by far the highest at close to 1,000 degrees. So at this point, you should now do some practice work. And the relevant exercise is labeled in class exercise number 14, dipoles and intermolecular forces.